If you look at how we used to model the heliosphere, the math seemed pretty straightforward. The sun constantly streams out a flow of charged particles called the solar wind, moving at roughly 1,000,000 miles per hour. We expected this wind to gradually slow down as it pushed against the interstellar medium, eventually reaching a point where the pressures equalized. But interestingly, when Voyager 1 reached about 113 astronomical units from the sun, the instruments recorded something that didn't fit the model at all. The radial velocity of the solar wind didn't just slow down, it dropped to nearly zero. I guess the question here is, how do you have a constant stream of particles from a star just stop? It's called the stagnation region, and it's a massive zone of space about 5.5 billion miles wide where the solar wind essentially bunches up and moves sideways. Scientists at the Johns Hopkins Applied Physics Laboratory, using the low-energy charged particle (LECP) instrument, found that the wind was being diverted, almost like water hitting a glass wall. But just so we're clear, there wasn't a physical wall there. The sun's outward pressure was being met by an invisible force from the outside that was much stronger than our best estimates suggested. And if you look at the data from that period, there was a strange lack of flow in any direction. For nearly continuous months, the spacecraft was sitting in a cosmic doldrum. This suggested that the transition into interstellar space wasn't going to be a smooth exit, but rather a compressed, high-density traffic jam of particles. It was the first real hint that the bubble we live in is being squeezed by the rest of the galaxy far more tightly than the textbooks, or rather, the previous consensus, ever predicted. In late 2012, Voyager 1 hit a region of space that theoretically shouldn't exist. According to the long-standing models, as soon as a spacecraft exits the sun's bubble, we should see a complete 180-degree flip in the direction of the magnetic field. This is because the interstellar magnetic field is generated by the galaxy at large, while the heliospheric field is tied to the sun's rotation. But interestingly, that's not what happened. The magnetometer data showed that the solar magnetic field remained perfectly aligned, yet the particle detectors were screaming. The low-energy charged particle instrument recorded a sudden massive drop in solar particles, down to about 1% of previous levels, while the count of high-energy cosmic rays from deep space spiked. It was a mismatch that baffled the team at NASA's Jet Propulsion Laboratory. If the magnetic field hadn't changed, how were the interstellar particles getting in? I guess the best way to describe it is a magnetic highway. It turns out the sun's magnetic field lines were actually connecting with the interstellar magnetic field lines. This connection created a porous transition zone where internal particles could zip out and external particles could zoom in, all while the directional alignment of the field stayed the same. But just so we're clear, this wasn't the actual boundary. It was more like a foyer. Scientists like Edward Stone eventually realized that the heliopause isn't a clean plastic wrap seal. It's a flickering, turbulent interface. If you look at the data from this highway, it showed that the spacecraft was essentially dipping its toes into interstellar space, while its body was still technically inside the sun's house. It forced a total rewrite of how we define the edge of a star's reach. We learned that you can be surrounded by the galaxy's radiation without actually being outside yet. If you look at the data from Voyager 2's crossing in 2018, you'll see something that Voyager 1 actually missed. Because the first craft's plasma science, PLS instrument, had failed years earlier, we were essentially flying blind regarding the temperature of the gas surrounding the ship. But when the second probe hit the heliopause, it didn't find a cold, empty void. It slammed into a wall of plasma so hot it shouldn't theoretically be there. The PLS instrument recorded temperatures jumping from roughly 11,000 Kelvin inside the bubble to between 30,000 and 50,000 Kelvin at the boundary. I guess the question is, how does the edge of a solar system stay that hot when it's so far from a star? It turns out this isn't heat from the sun, it's a compression zone. Imagine the solar wind acting like a supersonic jet hitting a wall of stationary air. The resulting shock compresses the plasma, and as you compress a gas, it gets incredibly hot. But interestingly, while the temperature is high, the density is still extremely low. If you were standing there, you wouldn't feel hot in the traditional sense because there are so few particles to transfer that energy to your skin. But for the spacecraft, this thermal barrier represents a massive pressure change. Scientists at MIT and the University of Iowa noted that this plasma wall is actually what defines the shape of our solar system. And if you look at the transition, it was remarkably sharp. Voyager 2 went from the hot, low-density solar plasma to the cold, high-density interstellar plasma in less than a day. But just so we're clear, this firewall isn't a permanent shell. It's more of a bow wave, like the water piling up in front of a ship's hull. The data showed us that our sun is essentially ploughing through the local interstellar cloud, creating a literal heat signature that we can only see once we're actually standing in it. If you look at the way we used to calculate the size of our solar system, we generally assumed the interstellar medium was relatively weak. We figured the sun's outward pressure would blow a massive, loosely defined bubble that only eventually gave way to the vacuum of the galaxy. But interestingly, both Voyager probes found that the interstellar magnetic field is actually much stronger than we ever anticipated. It turns out the outside is pushing back a lot harder than the inside is pushing out. I guess the question is, why does that matter? Well, a stronger external magnetic field means the heliosphere isn't a perfect sphere. It's lightly squashed, more like a blunt, rounded bullet. Data from the magnetometers on both craft showed that the interstellar magnetic field lines are draped over the heliopause like a silk sheet over a bowling ball. This draping creates a massive amount of magnetic pressure. Scientists at Boston University and the University of Kansas found that this pressure is what actually keeps the solar system's tail from being as long as we once thought. And if you look at the Voyager 2 data specifically, the spacecraft crossed the boundary at a point where the magnetic field was roughly 3 times stronger than the models predicted. This changed everything. It meant the heliosphere is effectively a pressurized vessel. But just so we're clear, this isn't just a physics trivia point. This magnetic pressure acts as a shield. It deflects about 70% of the high-energy galactic cosmic rays that would otherwise flood our solar system. Without this pressure paradox at the edge, the radiation levels on Earth would be significantly higher, potentially making life as we know it much harder to sustain. So, we've learned that the solar system isn't just a place. It's a structural entity maintained by a delicate, high-pressure balance between the sun's breath and the galaxy's grip. But interestingly, as strong as that grip is, the boundary isn't nearly as airtight as we thought. If you look at how we normally picture a boundary, we think of a container. Inside is the solar system, outside is the galaxy. But interestingly, the data from Voyager 2's low-energy charge particle instrument showed that the heliopause isn't a solid seal, it's more like a mesh. It turns out that solar particles, the inside of our bubble, are actually leaking out into the interstellar medium in massive, focused streams. I guess the question here is, why does a pressurized bubble leak? If you look at the magnetic data, the answer seems to be magnetic reconnection. This is a process where the sun's magnetic field lines snap and reattach to the interstellar field lines. When that happens, it creates a temporary doorway. Scientists at Caltech and the University of Delaware found that these leaks aren't just random. They're structured. Voyager 1 saw solar particles disappearing, but Voyager 2 actually caught them in the act of escaping. And if you look at the geometry of these leaks, they suggest the heliosphere has breathers. But just so we're clear, this isn't just a one-way street. As our solar particles leak out, galactic cosmic rays are leaking in through the same gaps. It's a constant, turbulent exchange of matter. This means the chemistry of the space just outside our solar system is being polluted by the sun, while our own neighborhood is being salted with heavy ions from distant supernova remnants. So, instead of a clean break, we found a messy, interactive zone. It's almost like the solar system has an atmosphere of its own that extends far beyond the edge. We've spent decades trying to find the line where the sun ends, but the data suggests that the sun never really ends. It just slowly dissolves into the rest of the Milky Way. If you look at the trajectory of both Voyager probes now, they are finally in the true interstellar medium, moving through a space that hasn't been touched by the sun's wind in billions of years. The main idea we've gathered from these last few years of data is that the solar system isn't a stagnant bubble. It's a dynamic, pressurized, and surprisingly hot participant in the galaxy's broader ecology. We've learned that the heliopause is a complex filter, a magnetic shield, and a thermal wall all at once. I guess the reality here is that we are running out of time to listen. Both spacecraft are powered by radioisotope thermoelectric generators, RTGs, that lose about 4 watts of power every year. We've already had to turn off several heaters and non-essential instruments just to keep the magnetometers and cosmic ray detectors running. But interestingly, even as their voices grow fainter, they are still providing the only ground truth data we have for the interstellar probe missions currently being planned at Johns Hopkins. But just so we're clear, the Voyagers won't hit another star for tens of thousands of years. They are currently passing through a local fluff of interstellar clouds that we only recently realized was there because of their direct measurements. And if you look at the future of these missions, they'll eventually go silent, becoming silent ambassadors carrying a golden record into a vacuum that we now know is far more active than we ever imagined. So, we're left with a picture of a solar system that is far more plugged into the galaxy than the old models suggested. It's a messy, leaking, high-pressure environment that protects us while constantly trading matter with the stars.